let's see if this marker works. Chemistry time. Let's see if this marker works. Today we're going to continue our discussion about light and quantized energy, and we're specifically going to be talking about, do you guys remember what I titled this yesterday? Something about electron configuration probably.
Electrons and electromagnetic spectrum.
Electrons.
Okay, and so we did get to both of those things. We talked a little bit about electrons in a very, very philosophical way, which I kind of got off on a rant, but I was very interested to talk about it, and I thank you for enduring that. Then we did talk about the electromagnetic spectrum, and that's kind of where we ended. We had a little bit of math with those. Let me show you two other kinds of math, and these should both be very simple, but today we're going to be primarily talking about electrons and electron configuration. We have two, I would say, very simple equations that we need to understand before we can talk about any deeper into electrons. We had talked about quantum mechanics yesterday, and the Latin word quantum actually comes from the same root as the Spanish word cuanto, how many. Quantum is something that can be counted. We use it specifically, usually, in science and math to mean a minimum amount. And in this case, when we talk about a quantum or quantum mechanics, we're talking about universally minimum amounts. So we're talking about a minimum amount. And we can represent the minimum amount of energy that it can possibly be gained or lost by anything is called the energy of a quantum. And the energy of a quantum is equal to Planck's constant times the frequency of that light or that electron or whatever that thing that we're talking about having a frequency. Remember, we talked about how frequency yesterday, we're using the de Broglie equation, we can think of everything as being waves. And when we get to larger scales, the wave nature is still true, but it manifests as physical matter instead. And that's something that we talked about yesterday. But we have this where the energy of a quantum, and this is also true of another thing where we talk about particles of light called the energy of a photon. A particle of light, which is both light exhibits what we call the wave-particle duality. Let's have a little aside over here. The wave-particle duality of light. We're going to watch today, if there's enough time after the video, we're going to watch today a little video that I want to, you can look this up on YouTube, but it's called the double slit experiment. Double slit experiment. And we're not going to talk about that right now because I won't do a very good job of representing it, and you can watch the YouTube video like we're going to about it. But this is an example of a manifestation of the wave-particle duality of light. What's duality? What might duality mean? What might dual mean? Not duel, not two. Yeah, two. Dual means two. A dually. You guys know about dualies. Let's bring this back to what the country folk know about. The dualies. Yeah, you know about a dually is something that has dual tires on each side of the axle. Not just tires, but wheels. Dual wheels on the back axle. So we have a duality of light, meaning that it has two natures. Two distinct natures. It's almost like, if you're familiar with the Trinity in Christian theology, the Father and the Son and the Holy Spirit, it's almost like that. Each of those things is the other, but it simultaneously is not. So light is a particle, but light is a wave, and a wave is not a particle. A wave is not a particle. So it has these two natures that are certainly different, but possibly even incompatible. It has two natures that are seemingly to us incompatible. They can't be both, but it actually is. It exhibits both the wave and particle nature. So we have these equations that describe that, and we call this particle nature of light, we call that a photon. A photon. On has kind of become like the suffix for particles in quantum mechanics. You know, we have protons, neutrons, and electrons. All of those things end in on. We also talk in especially particle dynamics in quantum mechanics. We talk about muons and leptons gravitons, those are theoretical, but photon comes from the Latin word for light, photos, same as photograph, or another thing probably. Photosynthesis is a good one, yeah. But photos is the Greek word for light, so a photon is a particle of light. And both of these equations have Planck's constant, which we talked about yesterday. And remember, it's not just a unit that we have where we know its value, 6.626 times 10 to the negative 34th joule seconds. And then we also have a frequency given in hertz. And so our energy in both cases, if we have Planck's constant given in joule seconds, frequency given in hertz, which is the same as seconds to the negative first power, what is our unit going to end up with as for energy? What unit will we end up with for energy? Joule seconds times seconds to the negative first power gives us, remember the negative first power means the same thing as 1 over second, so we're going to end up with what as our measurement for energy?
Joules?
Joules, yeah. Does it make sense for joules to be a unit of energy? Of course it does. That's the standard unit of energy in the SI. I need a really long cable or cord or something. I wonder if I have an HDMI cord or something. I'm going to show you something. I do. It's almost like I had this planned. I did not have this planned. I almost never have things like this planned, but I think this is a good idea. I'm going to erase this. Sorry. Are you good? Everyone have this written down?
Yes.
Where it gets kind of cool and funky is that light has this dual nature, wave and particle. But as I said yesterday, really every particle is actually a manifestation in the force fields that pervade the universe, and that manifestation can be thought of in the form of a wave. So we have this classic idea. I'm going to put that down for a second. We have this classic. Okay, rest in peace, headphone users. I guess that's the. I was saying, before we were interrupted, that we have this classical idea of, I still don't do that, and we still will use this model to help make things easier. We have this idea of, there's the nucleus, it's positively charged in general, and then we have these nice concentric circles around them to represent electron energy levels, which do exist, energy levels. What would we call this energy level? Sometimes we call them principal energy level. Well, what is this one? What principal energy level is this, do you reckon? 1. What about this one? 2. And what about this one? 3. And how many electrons can fit, in quotes, can fit in there is given by the equation 2n squared. Where if it's energy level 1, 2 times 1 squared is 1. So 2 times 1 is 2 electrons can fit. The second energy level, 2 squared is 4, times 2 is 8. 8 can fit in the second, etc., etc., etc. And these are quantized. They have a minimum energy level, and they are discrete. Not discrete in the sense that the word discrete, D-I-S-C-R-E-E-T, means maybe not sneaky, but like you're able to handle things without making too much of it. Like someone might ask you, can you be discreet? And then they might say, I put my dog down without my girlfriend knowing about it, or something like that. What that means, can you keep a secret? Basically, to be discreet means you can keep a secret. But this kind of discrete, D-I-S-C-R-E-T-E, means that it can only be in one of a certain number of states. So whereas we might have a continuous sliding scale of a ramp, this is continuous. A continuous electromagnetic spectrum, for instance, is continuous. You could be here. This is piece 1. You could be here. You could be here. You can move a half a millimeter back, and now you could be here, right? That's continuous. If you have a staircase, that's discrete. You can be here. You can be here. But you can't really, I mean, you know as well as I do that in real life you can be like half on one step, half on the other. But does the analogy carry? You understand what I'm getting at if I say that this is quantized or discrete. In real life, of course, you could be half a millimeter back on the staircase, but what I'm getting at is that this has certain states in which you can exist, and this has continuous state. This is kind of like the electromagnetic spectrum, but this is like the shells of an electron. An electron can be in the first energy level, and it can be in the second energy level, but there's no such thing as energy level 1.5. That does not exist. It cannot happen. Does not exist. It must be in one energy level or another. And when it gains, when this little guy, some EM radiation, some light is coming in, he can absorb, I shouldn't say he probably, it can absorb a certain amount of energy, a quantum of energy, a specific for that atom amount of energy, and that makes him go up to the next energy level, skipping right over the middle. And remember about electrons, it's not that he moves from one to the next. He stops existing in one and immediately exists in the next one. You remember that? They don't move around so much as they teleport. They stop being in one place and start being in another. And even that, just like I was telling you yesterday, even that is kind of a half-truth, half-lie that we tell people to help them understand it better. Because what I'm going to get at here is what's actually happening. So it can go from one energy level to another, and then when it loses that energy, it emits only a certain frequency of, we'll call it nu prime. It'll emit some frequency of light. And that's why when we put, for instance, calcium chloride into the flame test, it absorbs all different kinds, or it appears to absorb all different kinds of energy, although fire is providing a mixture of energy. But it's really only absorbing one certain frequency out of that. And then when it goes back down, it emits only that frequency, which we perceive as red for calcium. It's quantized. So we have this classical understanding, as I said, of the atom as surrounded by concentric orbits. We even do, and it's a misnomer, but we even do call the principal energy level sometimes orbitals. I will call them that. It's an understood vernacular that comes from the fact that we used to think they orbit like planets. We still call them orbitals sometimes, but we probably shouldn't. What it really is a wave. Who wants to be the assistant? I want to have it on camera so that whoever's missing, Tiana, come over here. Whoever's missing, stay off the camera if you can. What it really is a wave. So I have my HDMI cord here, and let's give it... Here, no, hold on it. Let's give it just a little bit of energy. Look, if we... No, hey, not you. I will do it. If we give it just a little bit of energy, you can see it has one node in it, right? So a little bit of energy is kind of like the first energy level. If we give it a little bit more... Oops, I gotta get this wrapped around my finger. You can see it starts to... Let me get this wrapped around a little bit better. It would work better if this were kind of more flexible. But you can see if I give it more energy, hold it still. You can see it starts to get 2 nodes. And if I weren't able to do it even faster, without knocking over my mic, it would get 3 nodes. But it might be easier if I draw it. But you get the idea. And you've seen that with things like ropes. That if we... Oh, this marker's dead. All my markers are garbage. No energy. We have a little bit of energy. Oops, that should not be wavy. This is supposed to be the baseline. More energy, we get 2 crests and 2 troughs in the same area. We get even more energy. Three crests and 3 troughs. So more energy means a higher, what do we call this about a wave? Do you remember? Frequency. A higher frequency, but also a shorter wavelength. And that's true of the electrons. And guess what? In our real-world example of the HDMI cord, I could probably give it a little bit more energy and just make this higher, but it's still only going to have 1 node, isn't it? And if I give it enough energy, it'll have 2 nodes. It's never going to have 1.5 nodes. That's crazy. That doesn't even exist. There's no such thing as that. So this is the way it actually is. What's this baseline represent? Well, what's permeating this entire thing and the entire universe? The baseline is the field force, the fundamental force of the universe, electromagnetism, that permeates everything. It's not the only thing that permeates everything, but there's an electromagnetic force field permeating the entire universe, including this atom. And when that field gets excited in this location has almost no meaning here, but when it gets excited in this little location, there's 1 node, and we call that 1 node an electron in energy level 1. If it gets more excited, the copper absorbs some energy from the fire, it moves to energy level 2, but it doesn't move to energy level 2. It now has 2 nodes in its little wave. And those eventually become shapes that we see of the shapes of orbitals diagram, which I love. And these are what we actually see on the, to the extent that we can see anything. But when we look at the scanning tunneling microscope image, these are the shapes that we see. We understand that they move in this way. Look at them. We have an s orbital. This is very quickly leading to the very next thing we're going to talk about, which will be the last thing we talk about in the main work for this chapter. But look with me on page 184. We have s orbitals. Do you see the s orbitals? What is the shape of the s orbitals? Let's diagram all of these.
What page?
184, I believe. What are they?
It's not in ours.
154. I'm sorry, I misread it.
What are what?
What shape are the s orbitals? Look at that little diagram and tell me what shape are the s orbitals.
Circles?
Yeah, well,
Spheres.
Spheres. It's three-dimensional, so they exist as spheres. But they're not solid spheres. We can think of them, the half-life I was telling you about earlier, is we can think of them as areas the electron can inhabit. But remind yourself, based on our discussion yesterday, that an electron is not really a physical lump of an object. It's a manifestation in a wave in a field. And so this spherical orbit really represents the harmony of that wave. That it's like this. This is the wave, or this is the electromagnetic force permeating the entire universe. This is the one-noded wave, and this is what it looks like in 3 dimensions. So whereas in my diagram of 2 dimensions, I have these 2 nodes. In 3 dimensions, it's a sphere. Same thing with the p orbital. What's that look like? Well, the p orbitals look like, we call this, sorry, I'm going to label these, we call this a barbell shape. You see the one there, the p orbitals look like, and there are 3 axes of this because, once again, whereas this is 2-dimensional, in 3 dimensions I can have this, or I can have it going up and down, or I can have it going in and out. Those are the 3 dimensions of space. And then with the d orbitals, it's the same thing, except now they manifest in 2 different directions. I'm just going to draw it like this. Oops, sorry. Now it manifests in 2 different directions. So where the p orbital is oriented on one axis, the d orbitals are oriented on 2 different axes. We call those clovers. And then there's also an f orbital. So what is this letter telling us? S, P, D, or there's an F. What's the letter telling us?
The orbitals.
The orbital, the what of the orbital?
The energy?
Yes, the energy. There are multiple energy levels. In addition to
Electrons.
the energy, and it's also, we call it the shape. We might even be better off calling it the waveform, but your book calls it a shape. So in the same way that my HDMI cord had this waveform, if I get enough energy in it, the waveform of these electrons in the s orbital is this one-node system. So we have an orbital shape, and that's in quotes.
Please excuse the interruption. All students have been sent an email. Please take time today to fill out the questionnaire. Thank you.
Well, I'm really glad that we got that mentioned. We have an orbital shape, which, remember, like I said, it could really be better described as a waveform. But what we use this for, and I'm going to erase this now, these are the actual shapes themselves. But what we use this for is this next bit, the main piece of work that we're doing, and this is where kind of the rubber meets the road, where all this loose theoretical talk becomes actually practical, and we can use it to describe the arrangement of electrons to the extent that it can be described in a particular atom from the periodic table. So what we first do is we have, let's start with hydrogen. One proton, let's say it's hydrogen 1, one proton surrounded by or orbited by, remember that's not how it really works, but this is a useful diagram. Just because it's not true doesn't mean we'll never use it. In fact, we'll use it a lot. But it's surrounded by or orbited by one electron. So what's the principal energy level of this electron? In what energy level is it?
1.
Oh yeah, 1. What shape would the orbital be at this level? Yeah, it's a sphere, so it's 1s. And how many electrons are there? 1. So this is the very most fundamental of what we call electron configuration. This is called electron configuration notation. What if now it's helium? Let's say it has 2 neutrons, don't really matter. Now it has 2 electrons. Well, what's the principal energy level of these electrons? What's the principal energy level of these electrons?
1.
Still 1. What's their shape? It's still S. And now there are 2 electrons. So that's helium's electron configuration. What this is telling us is that this is the principal energy level. This is the orbital, I'm going to put it in quotes again, shape. And this is the number of electrons. And that is the most basics of the electron configuration notation. We have run out of time, in fact, but there are 3 rules that we need to talk about still, that Aufbau principle, the Pauli exclusion principle, and Hund's rule, that tell us how to do this for more complicated elements. And then we're going to talk a little bit about valence electrons, but that is it. And this was not supposed to take 3 days, but there have been a number of interruptions, and mostly, I can blame it on the interruptions, but mostly it's because I like to rant about waves, I guess. Bye!